Good day everyone. Today we shall discuss Lesson 6, Linear Programming. This is the last topic to be covered by this course. There are three types of linear programming problem that we shall study under this lesson, namely graphical method, transportation method, and assignment method. But what is linear programming? Linear programming is a mathematical method of finding the best solution to a certain objective subject to a given set of constraints. In business, linear programming is finding the optimal solution to a certain objective function, which is usually maximizing profit or minimizing cost, when you are given scarce resources, which we call constraints. These constraints are expressed as linear inequalities, while the objective function is a linear function. So the first type of linear programming is the graphical method. This is a type of linear programming involving two variables, which uses graphing of linear inequalities to find the optimal solution. The optimal solution is usually maximizing profit or minimizing cost. Now, here are the steps in the graphical method. So, step number 1, we have here, graph the linear inequalities of the constraints to determine the area of feasible solution. The area of feasible solution is that set of points that satisfy all the conditions in the given constraints. Step number 2, we identify the corner points or the vertices. We usually call them the critical points of the polygon. Normally here, when you graph or when we identify the shaded region, the area of feasible solution, they are usually in the shape of polygons. So we identify the corner points of that polygon. Now these points can be identified graphically. When graphical identification is not possible, then the critical points can also be identified analytically using system elimination involving system of linear equations. Step number 3 means we have to compute for the value of the objective function at each of the critical points. Step number 4, select the point where the value of the objective function is greatest when you are solving for maximization problem, and the least value of the objective function for minimization problem. And last, you have to state your conclusion. Now, to understand this method clearly, let us take one example. Okay, the first example is shade example 6.1. Shade the region representing the solution set. The solution set we are referring to here is the area of feasible solution of the following set of inequalities. So here we try to recall what you have learned in high school when you are asked to graph inequalities involving two variables. So these are usually the constraints. They are expressed in this manner. So here are the constraints. 3x plus y is less than or equal to 6. 4x plus 3y is greater than or equal to 12. X is greater than or equal to 0. And y is greater than or equal to 0. So one way of solving this, if you have your, shall we say, a graphing calculator like Desmos, all you have to do is just type all the inequalities and you will see the graph as shown in the figure. So it is in this figure, yeah. So focus mo. So here you have your inequalities. You type your inequalities here, and you have the graph on the side. Now, this yellow shaded portion here, in the form of a triangle, represents the area of feasible solution. So, but the question is, how do we get these points, and how do we graph each of these inequalities? We can do this manually. Now, how do we do that manually? Let's take the first inequality. To graph the line, now this is the first inequality, 3x plus y is less than or equal to 6. So just get the equation, 3x plus y equals 6. To plot the line manually, you have to make use of your x-intercept and the y-intercept. Now, what do we mean by x-intercept or y-intercept? The x-intercept, if you look at this graph, refers to that set of points of the line that intersect the x-axis. So these are the x-intercept. Well, if you can see here, the value of y is 0. And what is the y-intercept? That is the set of points where the line crosses the y-axis. So these are examples of y-intercepts. If you look at the coordinates, the value of x is 0. So, to get the x and y-intercept, when we say x-intercept, y is 0. When we say y-intercept, x is 0. There. So, you have to get the x and y-intercept of all the equations or inequalities involving two variables. The other variable is, the other inequality is 4x plus 3y. So 4x plus 3y is greater than or equal to 12. So the corresponding equation is 4x plus 3y equals 12. Let's get the x and the y-intercept. Okay. Now, how do we get the x-intercept? Y is 0. All you have to do is just cover this portion here. So, when y is 0, you have 3x equals 6. So, what is the value of x? 3 times what number equals 6? Is 2. And how do we get x here? So, you cover this part. 4x equals 12. 4 times what number is 12? X is 3. What about the y-intercept? So you cover, x is 0, so you cover this part. Y equals 6. So this is 0. 3y equals 12. 3 times blank equals 12. 4. So if you look at your graphs here, you have it here. 2, 0, 0, 6. So this is the line representing 3x plus y equals 6. Then 3, 0, 0, 4, you have this line. And that is the line representing 4x plus 3y equals 12. What about x greater than or equal to 0? X greater than or equal to 0, the corresponding equation there is x equals 0. When you say y is greater than or equal to 0, the corresponding equation there is y equals 0. When you say x equals 0, when you are given an equation and you only have the variable x, the graph of which is always a vertical line. So when you say y equals 0, you are actually referring to y equals 0. When you say x equals 0, the graph of which is a vertical line. So you are actually referring to the y-axis. This is the y-axis. When you say y equals 0, you are referring to a horizontal line. And this graph is the x-axis. Next, let us now try to identify the shaded portion. How did we get this part here? Why were we able to say that this is the shaded portion? We were able to get 4 points, but we were not able to get this point. And how do we get this point? Looking at the graph, it is quite difficult to identify this point. So we have to do this analytically. So here, we have to make use of the analytical method of finding the intersection of the two lines. Observe that this one is the intersection of these two lines representing these two equations. So let's get the equation 1 and 2. Let's get the intersection. So beginning with number 2, 4x plus 3y equals 12 and 3x plus y equals 6. So we have to eliminate. We have to make use of elimination to find the intersection. To eliminate this is positive 3. All you have to do is multiply this by negative 3. So, multiply equation 1 by negative 3. So, each term must be multiplied by negative 3. What about equation 2? Just copy equation 2. So, if you multiply this by negative 3, you will get negative 9x, negative 3y, negative 18. Now, you can add the two equations. This one will give you 0. 4 minus 5, 9 is negative 5x. And this one will give you negative 6. So, solving for x, divide both sides by negative 5. You have negative 6 divided by negative 5, or x equals 6 over 5. Change that to decimal. That is 1.2. To find y, you can just substitute the value of x to any of the two equations. So let's say substitute x equals 1.2 in 1. Yes, it's easier to solve using 1. So 3x plus y is 6. So 3 times 1.2 plus y equals 6. So this one will give you 3.6 plus y equals 6. So y equals 6 minus 3.6. Y equals 2.4. So the value of the point of intersection now is x is 1.2 and y is 2.4. So now we were able to get all the points that we need to identify the area of feasible region. Next, how are we able to identify this triangle here as the area of feasible solution? Let's take a look at the graph. You can just evaluate. Say, for example, when you say 3x plus y is less than or equal to 6, this is the line, 3x plus y equals 6. There are two sides of the line. You have the left side and the right side. Now choose the point 0, 0. That is the origin, and here is the origin. Now you have to make use of a test point. So our test point is 0, 0. Substitute the test point in the inequality. If the inequality is true, then you have to shade that region where the test point is located. Otherwise, you have to shade the other side. So let us test at 0, 0. So 3 times 0 plus 0 equals 6. 0 is less than or equal to 6. Is this true or not? Well, as you can see, 0 is indeed less than 6. So this is true. So you are going to shade this region, this part. So you're going to shade that part. So you shade this part here. So this part is covered. Next, let us look at 4x plus 3y is greater than or equal to 12. At 0, 0, this will be 4 times 0 plus 3 times 0. Is that greater than or equal to 12? 0 is greater than or equal to 12. As you can see, 0 is not greater than 12. So this is false. This is the line representing 4x plus 3y equals 12. And here is your 0, 0. It says here false. So you will not shade this part, but you will shade the other side. So you will shade going in this direction. So as you can see, this portion is still covered. So what are the intersections of these two? It is this region here. Yeah. Including this one. Now, if you look at these two conditions, when you say x is greater than 0, let us look at the shade. You are representing all values of x going to the right of x. When you say y is greater than 0, you are representing all values of y greater than 0, so going up. So what is that common set of points? You are actually referring to this region here. So these two conditions simply says the first quadrant. So our concern here is only on the first quadrant. So taking all of this into consideration, that portion which is common to all is only this polygon representing a certain triangle. And these are the vertices. So now that we were able to identify the vertices, we have to go to step number 3. And what is step number 3? Step number 3, if you go back to the steps, okay, compute for the value of the objective function. You have to compute for the value of the objective function, if that is a linear programming problem. But for now, our main concern is only find the shaded region. So that is the first example. Let's take the second example. Okay, the second example here is find the shaded region. 5x plus 3y is less than or equal to 15. 8x plus 8 plus y is less than or equal to 8. Again, our main concern is just the first quadrant. So let us do that manually. So let's use the shortcut. Let's do it manually. So here is the manual solution. So the equations are, let's just graph the lines. 5x plus 3y is less than or equal to 15. The second one is 8x plus y less than or equal to 8. Okay, so if you're going to do this manually, get the corresponding equation. 5x plus 3y equals 15. And the other one is 8x plus y. So 8x plus y equals 8. So get the x and the y-intercept. Okay? For the x-intercept, so this is 0. 5x is 15. So x equals 3. For the second equation, this is 0. So 8x equals 8. So x equals 1. X is 0. So cover this part. 3y equals 15. Y equals 5. Y equals 8. Next, let's get the point of intersection of these two. So they will intersect. So to get the point of intersection, let us solve. So let's call this equation 1, equation 2. So copy equation 1. Okay, multiply equation 2 by negative 3. To eliminate y, this is positive 3. So to eliminate that, multiply equation 2 by negative 3. So times negative 3, that will give you negative 24x. Times negative 3, that will give you negative 3y. Times negative 3, this will give you negative 24. So this is equal to negative 19x. This is 0. And this is equal to negative 9. So x equals negative 9 all over negative 19. Or 9 over 19. Or the decimal equivalent of which is 0.474, as what you see in the graph. So we will look at that, we will look for this at the graph later. So for now, let us solve for y. So substitute x equals 9 over 19 into equation 2. This is easier to solve for y. So 8x plus y equals 8. So 8 times 9 over 19 plus y equals 8. So 8 times 9 is 72 over 19 plus y equals 8. So y equals 8 minus 72 over 19. So y equals, if you have your calculator, just compute 80 over 19, or simply 4.211. So the point of intersection is 0.474 and 4.211. In fraction form, you can write that as 9 over 19, 80 over 19. This is more exact compared to the decimal equivalent. So this is the point of intersection. Next, let's take a look at the graph. Ito. So here in this graph, you can see all the points that we have identified. 0, 8, 1, 0. Okay, this is equation 2. 0, 5, 3, 0. That is equation 1. This is equation 1. Now, this is the point of intersection. 0.474 and 4.211. Next, let us try to identify the region. Okay, 5x plus 3y less than or equal to 15 at 0, 0. Okay. So 5 times 0 plus 3 times 0 less than or equal to 15. 0 is less than 15. This is true. So this is 5x plus 3y. So the shade here is your 0, 0. So you will shade on this side. Let's consider the second inequality. 8x plus y is less than or equal to 8. So again, at 0, 0, 8 times 0 plus 0 less than 8. So 0 is less than 8. And this is true. 0 is less than 8. So this is the line representing 8x plus y less than 8. And here is your 0, 0. See, it is true, so you will shade this part. So what is the part common to the two inequalities? It will be this region here. Yeah. It will be this region, except that one, only this portion here. Since we are only referring to the first quadrant, as shown here by these two conditions, so you are going to remove this part, and this part is not included, of course, so we only have this quadrilateral. And you were able to identify now the 4 vertices. So that's the first step, and that is step number 1 when you are asked to do linear programming graphical methods. Now, example 6.3, you are now given the objective function. So in example 6.2, you are asked to minimize the objective function. The objective function is given as z is 10x plus 9y. Since we were able to graph the constraints as shown in, if you look at the constraints here, the constraints here are actually the inequalities that we have for the first example. So we just have to get the critical points of the first example. And the critical points of the first example are actually here. 1, 2, 3, 0, 6, 0, 4, 1.2, 2.4. So those are the critical points. So in example 6.2, okay, these are the points. 0, 4, 0, 6, 1.2, 2.4. Anyway, this is just labeling the points. You can label it in any order. Now let's do the computation. 10, 0. So how did we get, what did we get 10 times 0, 9 times 4? Remember, our objective function is 10x plus 9y. And this is your x and y. So 10x means 10 times 0. 9y means 9 times 4. So you add the two, you have this. Do the same thing for the other points. Since you are asked to minimize, according to step number 4, for minimization problem, you have to choose the lowest value. So the lowest value of z here is 33.6. So these are the values of x and y that will give you the lowest value of z. So what is now the conclusion here? So the conclusion for that problem is that since that is a minimization problem, then the lowest value is 33.6. So this is your answer, 1.2, 2.4. So conclusion, you have to produce 1.2 units of x and 2.4 units of y to minimize the objective function. And how much is the minimized cost, if that is a cost? So the minimum value is actually 33.6.